Okay, since we have a packed agenda, we're going to go ahead and kick this off. Hello, everyone. Thank you for joining the Khronos Roundtable on Open Compute Standards. Today's session will share preliminary insights from the Khronos AI Ecosystem Research Project, highlighting current industry trends and gaps, and will preview the forthcoming public release of the Khronos AI Research Database. Our speakers today are Neil Trevet, President of the Khronos Group, Markus Tavenrath, Khronos' Machine Learning Council Chair, and David Kanter, Peter Glaskowsky, and Victor Bittorf from Real World Insights. With that, I'll hand it off to Markus Tavenrath, Khronos' Machine Learning Council Chair. Markus?
Welcome everyone to our Building the Foundation for Accelerated AI roundtable meeting. Today's outline is, first we are going to talk about motivational purpose of our Khronos AI Ecosystem Research Project we are going to present today. The project is going to explore the problem why the AI acceleration ecosystem is so complex, and we are going to build a technical understanding why AI acceleration performance portability is so hard. Finally, we are going to talk about a solution exploration. How can open standards help to solve the problems we have uncovered? And eventually, we are going to have an open discussions where we welcome your thoughts and your feedback on the machine learning performance space. But first, let me give you an introduction of Khronos and its ML acceleration APIs. Khronos connects software to silicon. We are a non-profit standards consortium creating open and royalty-free standards focused on acceleration APIs, file formats for 3D, XR, AI, vision, and parallel compute. And our organization welcomes everyone to have a membership. We have about 150 members worldwide working on those standards. I am ML Council Chair and hosting the ML Council Group within Khronos, which is its internal forum to discuss ML-related issues and opportunity that affect multiple working groups. And yeah, we have a lot of working groups working on machine learning, including Vulkan, OpenCL, OpenVX, Slang, SPV, SYCL, and NNEF. And within the ML Council Group, we are discussing challenges in cross-platform ML development. We are promoting the exchange of knowledge in the machine learning domain so that everyone within Khronos knows about what's important in machine learning, so that we can build industry consensus on effective ML acceleration directions. And we are giving input to the evolution of existing API standards and extension, for example, in Vulkan and OpenCL, to ensure that they are going into the correct direction to accelerate machine learning, and also providing feedback to Khronos members and its API implementers. And to do all of this, we are conducting market research to understand the market. When I joined the ML Council Group, this was a slide which was quite famous. It's about the machine learning acceleration complexity. We have a few open source frameworks which are quite huge. And at the first glance, it looks like a simple market. But each of those frameworks is using a huge number of compilers, runtimes, and libraries. And each of those compilers, runtimes, and library, again, is using a lot of different acceleration APIs to feed hardware. And some of those APIs are Khronos open standards, but a lot of them are proprietary APIs like DirectML, CUDA, RockM, or Metal. But not on the slide, there's also a huge amount of NPU APIs where each and every NPU vendor seems to like to have their own acceleration API for their NPU. And we are starting to wonder about, okay, is there anything we can do to simplify the space to reduce the number of errors you see in the slide? And first, we have to answer the question, how can interoperability standards help? So as seen before, each arrow on the right side was essentially one proprietary API where a software compiler, library, or runtime had to implement one API to get to hardware below. So imagine you have 50 different NPUs and you would have to write a software with 50 different APIs which are non-connected, and you would have to maintain it. It would be a maintenance hell. You would have to spend a lot of resources just to ensure that you are hitting the market accelerators you're interested in. If instead there's an open cross-vendor API where multiple hardware accelerator vendors would implement this API, then a software developer implementing compilers, runtimes, and libraries would be able to target only this single one cross-vendor API and could spend the time on improving the library runtime or the compiler and bring more features in instead of having to spend time and money on maintenance and testing. And the Khronos has a lot of machine learning open standards activity to support this use case. First of all, we have NNEF, a portable ML model format and operator set, which now defines scriptnd in version 2 to define custom operators to build models. It turned out that having fixed operators only was not sufficient, and NNEF 2.0 tries to avoid this by being just defined by custom operators. We have Slang, which is a modern shading language, and also an open source compiler with type reflection, specialization, and auto-differentiation, which gives you the backward pass in machine learning for free, which is perfect for neural graphics. We have SPIR-V, an hardware-agnostic GPU-AI compiler target with intrinsics to map matrix ops efficiently onto tensor cores. And quite new, and not a lot of people might have noticed, there's also now a tensor graph API, tensor graph IR within SPIR-V with tensor operators to not have just shaders, but also graph within SPIR-V. And then we have Vulkan and OpenCL, which are both cross-platform execution APIs with portable management of shared memory synchronization, tiling, and those have also been expanded by tensor intrinsics and operators like cooperative matrices for more efficient gem implementations. And with all of our machine learning standards, we managed to get adopted by a lot of ML runtimes and compilers which ship today, and they leverage our APIs to have good backend acceleration, like PyTorch with ExecuTorch, GGML, Alibaba, Tencent, Irie, and so on. With all of those Khronos APIs supported by so many ML runtimes and frameworks, we still think we can do more to streamline the ecosystem. So we got some initial feedback where we started like, okay, we are not always performance portable. And so we need real world feedback now to guide our next steps to improve our APIs. And questions which arise are like, are the current Khronos APIs providing effective acceleration in practice? What are emergent effective directions for the ML acceleration stack? Or what can we do for open standards to do genuine ecosystem benefits? And can we finally crack functional and performance portability? And to get an answer to all those questions, Khronos has initiated the AI Ecosystem Research Project to better understand market realities. And we like to thank FutureWay for sponsoring this project. And now I hand over to David to talk about the research project.
All right. Thank you very much. It is my great privilege and honor to be speaking here. All right, and we're in slideshow mode now. So, first, by way of introduction, my name is David Kanter, and I'm leading this fantastic team at Real World Insights to help execute this project on behalf of the Khronos Group. Just brief sketch here. Myself and my colleagues, Victor and Peter, all have extensive experience in graphics, machine learning from both the software and hardware perspective, which is really great because this project is really at the nexus of software and hardware, as is befitting the Khronos Group. I was one of the co-founders of ML Commons, where I currently lead the MLPerf benchmarks. Those are the industry standard benchmarks measuring the speed and energy efficiency of AI performance for training and inference. Particularly relevant here, both Peter and Victor have worked at various companies that build, deploy, machine or use machine learning acceleration tools. So just really fantastic experience in this vein. Again, the goal of this project is to look at what are the opportunities for the Khronos Group to help make machine learning acceleration more pervasive, which in turn will empower the community and the whole world to see more benefits from machine learning. So why is the ecosystem so complex? What are the problems? Our approach has been to interview experts at all levels of the stack, really, from uh, the lowest hardware level. So many Khronos Group members that produce intellectual property or systems that are responsible for executing machine learning, all the way up to, at the highest level, folks who are building applications around AI or employing AI-driven features. And that includes many important constituents in between, such as AI model developers, people who are working on tool chains, as well as horizontally other elements of the open source and standards community that are critical in the machine learning ecosystem. And so we set out to explore through one-on-one interviews, informed by our expertise, informed by broad solicitations, to get their feedback on what are the problems here and what can we do to help. And actually, some of the best news is that it is very clear that we saw one predominant problem here, right? 85% of the folks that we talked to said that, the core problem is we've got too much manual expert work when it comes to AI, when it comes to launching AI products or features or maintaining them. It's simply too much expert work. And this is great, right? The Khronos Group is a community of engineers. And, one of the things that is a fabulous outcome is when you do see that there is a single problem that constitutes the bulk of the challenges. And so that's a good situation to be in. Generally speaking, what we found is that issues around performance, portability, and expertise kind of fell into three buckets, or use cases, really, which we describe as one-to-one, one-to-many, and many-to-one. One-to-one, you can think of this as roughly mapping onto a fully vertically integrated kind of solution, where you have one platform and one model, and that's really all you care about. Now, this is the easiest case to optimize. However, I would point out that actually this tends to quickly morph outside of one-to-one, right? If we were to take an example like Tesla, where they have full control over their whole stack, including hardware, if as they have been successful, they have more hardware platforms, right? Over time, the one-to-one use case morphs. And generally, it tends to morph so into the one-to-many, where you now have multiple platforms, right? And this is a very common situation that a lot of AI model developers and application developers face. Now, it could be very similar platforms, maybe different generations. It could be two different platforms for smartphones, say Android and iOS. Or it could be, two wildly different platforms like the data center and a client system. Sort of conversely, many platform makers face the challenge of how to map multiple models onto a single platform efficiently. Now, all of these are solvable, as is, sort of the worst case of many to many, but it requires a huge amount of manual work by experts. And I think that one of the core challenges is we simply don't have enough experts to get all of this work done. Another insight that we gleaned that was, again, very helpful is that we should really be focusing on inference. It's the more significant opportunity for a number of reasons. First of all, it is a larger market. And counterintuitively, training is a little less performance sensitive. cutting edge training systems in many cases have extremely long run times, even for very small networks. You know, anecdotally, I talked to someone who works on networks for smartphones that have very low runtime, and they indicated that they prefer to have many training jobs going concurrently, and that the runtime still might be many, 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 many hours, such that even a small improvement in performance isn't really noticeable. Right. Uh, Additionally, training is sort of fundamentally an R&D operation. It's very fast moving and therefore hard to standardize, right? People purposefully want to explore a wide range of options with very bespoke systems. And so standards simply may not add as much value there. In contrast, the diversity for inference creates much more of a pull and value proposition for standardization. One of the concepts that quickly emerges being critical here is speed of light, which I want to define and then kind of discuss the relevance and importance and the challenges associated. So speed of light is the way that we generally tend to think about it is what's the best possible performance end to end or of a model on a given system. And one of the bold claims here is this claim in red, which is that every inference value chain is eventually going to be looking at speed of light. Now, not everyone necessarily has explicitly identified that. Um, and but in reality, it actually does crop up. And those who have not explicitly identified that, in some senses, are delegating this issue lower in the stack. And so the way that the speed of light actually becomes critically important is generally driven either by cost or KPIs. So on the cost side, if you can significantly improve the cost profile of your platform, you can expand your target market, right? If you can take a network that required a dedicated workstation and now run it on a smartphone, that gives you many more potential customers. Or if you are deploying, you're selling a product that's both software and hardware, you can reduce the cost of the hardware. That's sort of one side of the equation. The other is oftentimes performance will unlock new features, right? Which is critical to, again, adding more value into the ecosystem. We want a new feature in an application. It has an AI model or many AI models associated with it. How can we get all of those to run? There's also sort of the competitive landscape that tends to want people to be even. Maybe there's a feature only available on one platform. Well, we want it on our platform too. Also, reducing power can be a great driver, right? As performance increases, oftentimes power efficiency will increase in tandem, right? And so over time, these pressures all tend to make speed of light an important aspect of the business of AI, even if it's not explicitly mentioned. Now, I will say that the majority of folks we talked to did say that it was a top-line consideration as well. So let's dig a little bit more into the speed of light. What's good enough? If you ask me for a single number, as the chart shows, I'd say it's about 80%. But in reality, it's a complex spectrum. And, for a lot of R&D efforts, simply getting something running under 50% might be acceptable. Think of, AI applications where they're not a big portion of the execution time, prototyping, et cetera. Then there's sort of this 50 to 80% zone where time to market is an overriding consideration relative to performance. But typically 80% is sort of cited as the minimum that folks want. Many people want higher, closer to 90, 95%. And then, I would say that anything beyond 95% is both incredibly difficult to achieve. And there are folks who articulated a desire for this. They're typically from companies that have very large scale engineering teams working on, incredibly high value problems. And they might be willing to deploy a team of 10 to 20 engineers solely to improve performance from 95% of speed of light to 96% of speed of light. But those are the most extreme problems. Those are the most well-resourced teams. And in many cases, they're willing to move well outside of a standard in order to do what they need to do to achieve that performance. So, again, dialing back, we've got a distribution of acceptable levels of performance, but the most common threshold that is cited is about 80%. So what makes the speed of light hard? I'd pinpoint these 5 concerns that we saw. And some of them we'll talk in a little bit more depth in some later slides. But briefly, within end-to-end AI applications, typically there's some amount of pre and post processing. For those familiar with computer vision, this might be something like image resizing or scaling. And that can be sometimes half of the overall execution time, right? And that means that in conjunction with considering the AI inference, the pre and post processing absolutely must be considered. Data movement is a top concern for performance. A lot of the expert work that's performed is focused on reducing copies of data to and from memory, reducing buffer copies, reducing trips to the network, et cetera. And this is an area where a lot of experts spend a lot of time optimizing. Architectures often will need to rewrite the graph of a neural network in order to get good performance. And again, this can take a lot of expert time. Another critical factor that we encountered is the extensive use of custom operators. We'll again talk about this in a little bit, but custom operators are specialized logic operations that may be specific either to a model or to a platform. And one of the key challenges is by introducing these new operators, the compiler and system support will lag behind, sometimes 6 to 12 months. Sometimes it'll never show up. And that can make supporting these custom operators very, very challenging. And then there's an overarching concern of quality, right? Which is like computer graphics, quality is somewhat of a free variable in the context of AI, and optimizations can impact quality. And quality is extremely difficult to quantify or standardize. So I want to pause here and restate the problem explicitly, and I think this is actually a very important and valuable exercise here, which is how can we get portability for AI models given the desire for speed of light, and what can we do to really reduce the amount of expert work necessary to deliver that? So that is our problem restatement. And now I want to dive into a bit of the technical underpinnings around that challenge and problem. By way of example, I want to explore sort of performance portability. Let's take a sort of simple neural network like YOLO. This is a convolutional neural network used for computer vision. And let's imagine we've developed it on a first system. We're going to run it on a second system. And, in general, this network is primarily composed of convolutions and activation functions, specifically the rectified linear unit, or ReLU. So let's just imagine we've gotten an Onyx graph, and that it contains our ReLUs and our convolutions. Mathematically, there are a number of different ways to express this common motif. If you're extremely lucky, maybe your platform has built in a fused convolution and ReLU operator, as you can see on the top. Maybe it has a separate ReLU and convolution operator, maybe just ReLU. But ultimately, whatever your platform does support, a human or compiler is going to need to select how to express this math on that platform. That requires a considerable amount of expertise and is quite challenging. Turning to custom operators, one of the things that we found is that new popular models often have a third of their operations are these custom operators, right? So this is something that is not defined within a standard authoring framework and instead is implemented by the model developer as part of the development process. And what that means is that the humans or the compilers, the experts, will not have seen these custom operators. Now, sometimes they may exist as a function of the platform, but again, model developers may not be aware of them. And so, these custom operators are extremely challenging to work with, but because they are so common, they're extremely important to handle correctly. Now, there are some tool chains, such as OpenAI's Triton, that allow very quickly and efficiently writing operators. But one of the things I want to stress is that in our discussions, that operator performance isn't portable. The operator functionality is. So, it can be quite possible to write functional operators that will work on multiple platforms, but the performance will not be sufficiently high to get us close to the speed of light, right? And so the existing tooling, isn't sufficient given the speed of light desires that we have within the ecosystem and community. Broadly speaking, many platforms might have different scheduling and assignment opportunities, very common compiler problem. If you consider a platform like a smartphone, you've got many different ways that you can execute a neural network, right? It could potentially go on the CPU, on the GPU, maybe on the NPU. Picking where to execute which portions of a neural network on which blocks, again, requires a human expert or compiler to make that choice. The knowledge of how to make that choice requires such platform-specific expertise that today that expertise is really only in the platform vendors themselves and maybe the most well-educated developers who are intimately familiar with their hardware platforms and have extremely good access to the hardware vendors, right? There's so many special cases that this just becomes extraordinarily difficult for the ecosystem. Turning to pre and post processing, a typical end-to-end inference flow might look like this. So if we were, and before doing inference, there are these pre-processing steps, and then afterwards you have post-processing prior to the output. Oftentimes pre and post-processing is either model specific. So for example, for an NLP model, typically you will be tokenizing and detokenizing. Additionally, on the post-processing, you might be looking at the response of the large language model to filter out certain keywords or put in various guard bands. And so there's a lot of non-inference computation that is part of the application. Now, the great news is that for a lot of things like computer vision, we do have some very rich, powerful libraries that can help here. But that does not solve the more general case. There's many different types of data, many different types of models, and there are also platform-specific pre- and post-processing steps. So, for instance, choosing to transpose a data structure in a particular way is platform-specific. And unfortunately, the pre- and post-processing often ends up falling back to the host processor, which creates an opportunity for acceleration. Quality. Again, we've talked about this. I wanted to highlight it with an example. Many of us have seen image generators, right? Text-to-image models that when asked to produce an output, produce something that fails. So I picked out an example here where many of us are familiar with. A lot of these image generators had difficulty drawing hands initially. And so the key point I want to make here is that fast and wrong is still wrong. And evaluating correctness is really, 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 really hard. This is a core problem for a lot of application developers. And so anything that makes correctness more difficult is extremely challenging. And a lot of these performance optimizations can have some quality trade-offs, right? And so some of the barriers of adopting newer numerical formats that give us better precision, like FP8, like FP4, are very much limited by the ability to deliver good quality. So some of the other insights that we got and perspectives that I wanted to surface are sort of on the left portion of this slide, right? Which is, don't, the AI marketplace and ecosystem moves so fast so that anything that happens, you have to be able to adapt to new technology. People are thinking in terms of weeks, not years. And so don't allow things to stagnate. There are authoring frameworks that are extremely large in terms of the number of operators that they support, and that's really problematic. Too many operators means too much difficulty in supporting them all from an acceleration standpoint. There are a lot of operators in PyTorch, just as an example. Supporting all of them is practically impossible, even for the most well-resourced of organizations, right? Let alone startups or platforms that are in early stages of bring up. So don't build something with too large of an operator set. Also, don't create the union of functionality of many technologies. Again, folks specifically identified this as too broad. And really what they said in some ways is a clear and opinionated approach is actually what's needed. Not creating infinite possibilities, but pointing out what is the right way to go and being crisp and clear about it. And so I'd sort of summarize this by saying, that the next set of standards around ML really need to reduce confusion, not add to it. There were a number of ideas that have come up during this process that we'll talk about in a little bit more detail in the solution section. But I want to call out things that were mentioned. Some of that is expanding shader intrinsics to include operators like convolutions and gems that are really common. Looking at different IR graphs and operator sets, as well as the greater use of AI for optimization. So now I'm going to turn it back over to Markus, where he can talk us through some of the solutions about how AI might be able to help the ML ecosystem. All right, Markus, take it away.
Thank you, David. So let's talk about the solution exploration we have done so far in the ML Council. Okay. The first obvious solution to machine learning is compute shaders. So compute shaders are widely supported within Khronos API, Vulkan, OpenCL Circle. Vulkan itself is now widely supported by GGML, TVM, IRE, Executorch, and more frameworks, meaning, well, we did a good job. We enabled machine learning with Khronos APIs, and we also added a series of extensions to implement machine learning operations, especially for matrix multiplications, like the cooperative matrix extensions, but also integer dot products and matrix vector multiplies. And in addition to this, we also enhanced the number of supported data types within shaders to float 16 mass, int 8 mass, bfloat 16, and fp8. But the problem with compute shaders is it's all responsibility of the developer to implement each and every operation. So for each framework, every operation must be implemented. For each hardware platform, and every operation must be optimized if we want to get to speed of light, or at least 80%. And each IHV, and we have k IHVs, for each IHV, one or more platforms can be released each year. And now you are one of the developers working on multiple platforms, so you would have to maintain m times n times k permutation of the same operation and update it potentially every year. Some of them are more performance sensitive than others to ensure that you have an efficient running framework. Experts are rare, so it's really hard to ensure that compute shaders are the solution forever. But they're extremely good for research and for operations which cannot be supported by specialized hardware yet. And yeah, just to give you information, if you're optimizing, you have to see register limits, shared memory limits, cache sizes, number of cores, threads per core, vectorized instruction, multiple extensions for cooperative matrices, and so on. So it's an immense optimization space you would have to do manually, and each and every framework is currently doing this optimization space. So the next method which comes to mind to relieve developers from shaders would be meta commands. Yeah, you define an API with a fixed operator set, but you don't define any connectivity information. Each operation is just an entry in the command queue. And yeah, because you're not specifying any op dependencies, besides having barriers between the operations for memory consistency, the driver is not able to fuse any of those operations. And if there's no operation fusion available for performance, then you have way more data movement than required. Data movement means energy and time, so you're not getting to speed of light. And as soon as you are starting to expose fused operators inside your operator set, you are growing an overly large operator set, and eventually will have a lot of trouble supporting an exponential number of operations inside your driver. Still, meta commands are supported in OpenCL by a Qualcomm operation extension. So if you really want to have maximum responsibility by the driver to be able to optimize the full machine learning graph, you would have to define some kind of fixed operator set and pass a full neural network to the driver and not something in between. And so the driver can decide about the implementation strategy. Depending on the hardware, maybe having simple kernels is good. Sometimes you want to do fusion, for example, by a gem and an ReLU. Some drivers might even be able to fuse multiple gems together, or gems and convolutions. There are a lot of different ways to implement the convolution, which depends on the hardware underneath. And you could even use special hardware like NPUs if you have the full graph for certain operations, but use the GPU for other operations. And with regards to performance and portability, a graph support would be future-proof with support, because if a new platform will be released, the idea is that there will be a new driver, and the new driver will support the whole new platform and knows everything about the platform and delivers the best platform details. But it's also most work by IHVs and requires rigorous conformance testing to ensure that each and every platform really operates correctly on the graph. And to minimize the amount of effort each IHV would have to do, we have to think about a trade-off between driver and offset complexity. If we would have an extremely huge operator set like Onyx, which gets enhanced quite often, then drivers might fall behind in implementation, or if you have a new application which uses a new offset, the driver might have been updated on your platform and you cannot use a new offset. So the goal is really like, can we find a minimal offset which can be used to define a more complex offset and which can be is optimizable at the same time, and then we can define subgraphs for more complex operations via passing to the driver and maybe even having libraries of subgraphs to get to a place where we get the comfort of high-level ops, but not requiring the driver to implement each and every high-level operation. And ARM just released the ML graphs extension on Vulkan. Take a look at VK ARM tensors, VK ARM data graph, and ARM is proposing TOSA's operator set for such a graph support. But the problem here is still, how do we handle custom operators? And this makes us wonder, would it make sense to define a hybrid, some API where we would have a minimum amount of really hard to implement or really hard to performance portable implement operators like German convolution, but have everything else in some kind of custom operator language like scriptnd from NNEF2, so that we can give more flexibility to platform vendors. Or do we need a richer operator set? And if we have something like this hybrid graph, assuming we would do it, could we give hints from the platform to the compiler in the background how to optimize? Or should we provide a library with high-level ops for such a platform? And if we have such a library, would it be okay if drivers could shortcut operators of this library? All of those are questions we have to the ecosystem, and we would really like to get your feedback. Also, some people are wondering if we can use AI to drive the performance optimizations by compilers. Assuming the compiler is not within the driver, but we have TVM IRI, for example, taking a graph and compiling it to Vulkan shaders, they have to know about the platform to generate the most efficient code you can imagine. And they need to know about the platform. And this means you have a time capsule. At some point, you have an IRI version now in your platform. It can optimize for this platform. 1 year later, a new version of the platform is getting released. IRI doesn't know about it, and your application is not getting updated. So it won't be able to optimize for the new platform. Can we find some solution where a platform could give information back to the compiler, telling it, okay, use those techniques, and then we get efficient code? And what hardware metadata would we need to supply for this compiler optimization? This is a potential area we should explore. Do you think it makes sense that we try to find a consistent method for hardware to describe itself to compilers, so that compilers like TVM and IRI would be able to know about tile sizes, the number of LUs or MAC units, the SM size, cache hierarchy, memory bandwidth? All of those are informations which experts use to optimize their code to run as efficient as possible on their hardware. If we can give this information to a compiler and maybe an AI-driven compiler, can we make compilers which can get close to human performance when it comes to just-in-time generation of code or not? And if we have this information, how do we provide it to the compiler, and how would we achieve a critical mass to drive adoption? So I want you to get involved. We have so many questions in which direction we should go, and we want to ensure that we are going into a direction which really helps the ecosystem make better software for machine learning. And we are collecting online survey responses. We have a QR code on the slide on the lower right. Please scan the QR code and take a few minutes to give us your views. This would be great. And one of the questions in the survey is if you would be open to one-on-one interview. If you are an ML developer, please say yes, so that you can talk to David's team and give your input to our research project to improve our database. Also, we are going to give a Birds of Feather at SIGGRAPH, August 13th, 3:33 p.m. Pacific time. If you are in Vancouver, please come talk to us in person. You can ask us questions over there. You can tell us everything you want to. And join the Khronos ML forum for ongoing updates. Thank you for your time today. And now we are going to questions and answers.
Yeah. First of all, thank you all for taking the time to join us. There's a question that came up about 20 minutes ago. I'm going to just read the question and then try to go through and provide a little bit. I'm going to respond actually with a question. So, do you treat APIs for AI compute on GPUs with tensor cores as separate from APIs for driving AI on dedicated discrete NPUs? What's your long-term approach to standardizing APIs for AI compute for these? Vulkan or OpenCL. The divergence between OpenCL/CUDA and Vulkan for AI compute is a pretty big pain point for practitioners. So I think that, I agree that that is a pain point. That is one of the things we are looking at solving. And in particular, how can these things potentially be used together or, pick from one, right? That was one of the challenges that was alluded to rather explicitly throughout the presentation. So, if you have a particular perspective on this, we'd like to hear from you, but it's good to know that the pain point that you're identifying is actually, resonates with the work we've done. One of the areas where I think actually some input would be great is folks who are doing AI compute within graphics applications. So if there's anyone in the audience, for instance, from some of the game engines and have thoughts on this, that's feedback we'd in particular love to see. So, I see there was a second question, and hopefully for and so there was another vote for AI compute plus graphics is fairly important. So I think this is fantastic. This is exactly the kind of feedback we want to get. So if this describes you, please, could we actually go to the prior slide where we have an email address for how to get in contact with us? We'd love to hear from you via survey, if you'd be available for a one-on-one interview. All right. So there's a question from one gentleman about accessing the slide deck, which will, I believe, be sent to attendees after the fact.
And we have a second question there. Do you want me to read it out or?
Yeah, I will read it out. So it was stated that inference represents a potential opportunity for standardization, but training less so. Is this purely technical in nature, or why wouldn't open standards help researchers who are working on training iterate more quickly and effectively reuse their know-how? Or is it a commercial consideration that training hardware is a high margin product and hardware vendors would prefer vendor lock-in and proprietary APIs for training hardware to protect their business? We have a slide specifically on that. I think what I would say is there's a combination of aspects here, right? So one, just to recap the slide, what we found is that the speed of light, and I think, Markus, I want to say it's like maybe the third or fourth slide in my section, but yeah, we should just go back to that while I'm talking through that. Yeah. Right before speed. Yeah, there we go. Training versus inference. Right. So dialing back, I think when I look at training versus inference, I actually think of a good analog for those of us is training is like compiling an application. You do it once, but then you run it hundreds of millions of times. And so you think about something like Microsoft Office. Yes, you want to compile it to get really good performance, but the energy expended on compiling Microsoft Office is dramatically outweighed by the energy and the value created by running Microsoft Office. That's sort of a conceptual example to sort of illustrate one reason, which is inference is a larger market in the long run than training. Then there are several technical considerations here, right? One of which is that training simply moves so fast. There's so many speculative and experimental techniques. The point of training is to be trying out new models, new model architectures, and where high velocity of change is sort of intrinsic to the nature of the activity, that does tend to impede standardization to a certain extent. So there's sort of an impedance mismatch between the nature of training and standardization there. And also, one of the things we did see is that there is a lot of work on, very bespoke systems that are highly specialized there, as well as the performance wins are less dramatic, right? That second bullet point, which is that according to some of the folks we talked to, training performance sensitivity is somewhat lower than inference. So if you have a counter view, this question came from Eric Tomask. We'd actually love to hear from you and hear your voice. So again, I would encourage you to engage with us. But thank you very much for that question. And then I see one of my longstanding friends and colleagues from the MLPerf community, Mark Charleboy, commented that taking an approach for an opinionated minimal operator set seems counter to the reality of the rate of change of AI models and custom operators. Right. And I would agree, right? The feedback we got was both, hey, we need custom support we need support for custom operators, while at the same time, we want a narrower band of operators to support. So I think that is something that, we'd, again, like to hear from folks on. How can we satisfy those twin desires, right? Is it possible that custom operators and that good support for custom operators in an open standard might allow for shrinking the size of the default operator set? Is that a possibility? Or maybe it's a non-starter. Again, I don't disagree that those things seem to be in tension, but it is something we'll have to grapple with.
Yeah.
And thank you for the comment, Mark.
And it's quite important to note that having a huge operator set in a driver means large drivers, and also it will take a long time to get a new operator into a driver. The machine learning frameworks today, if they want to have a new operator, they define it and they implement shaders, and everything works quite quick. You can ship the new framework, the new runtime. If you would rely on a driver to ship a new operation, then it can be 1 or 2 years if you are unlucky, and then it's too late for the new operator because 10 new operators have arrived. If we are going to move the optimization problem to the driver, we have to ensure that we still can move fast. And moving fast with a huge operator set where each specialized version is implemented is unlikely. We have to think how can we build the building blocks so that you can build all your operators as fast as possible.
All right.
One more question.
Great question. So I'm going to read this one. When you mean inference, for what class of hardware do you refer to? For example, PCs, cloud systems, laptops, smartphones. So I think we can stay on this slide. Right, so inference is significantly more diverse than training, as the questioner has pointed out. I think producing a standard across all of those things may be somewhat challenging. And so I think one of the questions is not can we make, one standard to rule them all, and perhaps that's possible, but is there a subset across which this might be tractable? Right, and it could be, for instance, maybe only laptops and smartphones and PCs. But I think that is one of the implied questions, and it is a great question to be asking. What is the scope of the standardization? And by restricting that scope, will it potentially allow us to truly standardize?
Right. So one of the problems is the software deployment problem. We have a huge amount of software deployed on smartphones, laptops, PCs, and also cloud. But we want to ensure that deployment of software with inference will be as easy as possible and just runs on the maximum number of hardware you can imagine. Deployment in cloud is desirable, but cloud you have less variance in the systems than on a smartphone or the laptop or PC. So the higher the variance is in the ecosystem, the more important it is to get a standard established, to have end users not having to worry about which of the hardware I'm going to buy, so that my application of choice does run.
All right.
I think
We've
we
got
time for just one more question. There's one more coming from Anita.
and this is from Anitha Natharajan. How will Khronos standards ensure portability and performance across rapidly evolving AI hardware platforms? I mean, that is the question before us, right? That is the question that we are at a high level attempting to answer. And so, I look at this as an information gathering exercise to help us make that decision. Markus, anything to add? Or particularly, I would look at those solutions and see if one of them resonates with you.
So Khronos standards ensure portability through conformance testing. So if anyone implements a Khronos standard and wants to have the Khronos standard label on their product, they have to show that they are conformant to the standard, and this is how we ensure portability. How to manage rapidly evolving AI hardware platforms. This is our information gathering. How can we define a standard which doesn't get obsolete within a year?
Yeah, I mean, it's a great question. That is actually the core question. Is it too soon to standardize if everything is moving too fast? I mean, that is one of the questions we're trying to answer. But I think in the longer term, a really successful standardization exercise, it's not just the hardware vendors throwing potential solutions at the software community. It's the software community and the hardware community working together to try and converge with consensus on a set of functionality that both communities can live with, and over time figure out how to converge to streamline the development from both the hardware and the software side. So standardization is a cooperative process. It needs everyone's involvement.
Absolutely. And I would, just to emphasize one of the things Neil said, there's what is the right point for standardization is absolutely an intrinsic part of this. And it may be that the answer is not today, and we need the temperature, the rate of change, the velocity to decrease a bit more. That's one possible outcome. So I think we're at time. And I guess I want to close by saying thank you so much for taking the time to join us. And I hope that you will reach out if you have if you think you can add insights to this process. Markus, Neil?
I'd like to thank everyone as well for joining and taking the opportunity to listen to what we found.
Excellent. Thank you, gentlemen, for the presentation. We appreciate your time and effort in putting this together. And as everyone, thank you for joining us today. As a reminder, a recording of this presentation along with the slides will be available on the event webpage, and a direct link will be sent to you in a follow-up email. Please take the time to complete the survey. Your feedback is very important to us, and have a great day.